Alrighty guys, today we're going to talk about two different things, actually three different things. We're going to discuss the rest of chapter 17, which has to do with electric fields and how to draw field lines, and we're also going to discuss something called electric potential energy and electric potential. So the first part of this PowerPoint is going to be discussing electric fields. Now it kind of makes sense that every charged particle has a field that surrounds it. It's when another charged particle gets close or inside of this field that it will encounter an electric force. So you kind of got to think of electricity a lot like gravity. Every planet has its own gravity, has its own gravitational field. When another object gets within that gravitational field, well then it starts to experience the effects of the planet's gravity. So electricity works a lot like that in many different ways. It works like gravity, and we're going to see a couple of other examples of that later. But the strength of the force that this charge is going to experience depends on the field that that first charge emits. So if I have two little charges here, this guy has an electric field coming off of it, which we will learn how to draw the lines here in a second. They don't look like this, by the way. This guy's either going to feel an attractive force or he's going to feel a repulsion force between him and this other charge, depending. If this is a positive and a negative, he's going to be attracted towards this charge. But he experiences that force when he enters this guy's electric field. So, when we talk about charges and how they interact with one another, it's helpful to draw what's called electric field lines around the charges. Now keep in mind that there's not actually, change the color of my pen, there's not actually lines coming out of charges. I don't want you guys to think that there are these little protons and electrons flying around with big old sunbeam rays coming out of them. It doesn't work like that. It's just a way to visibly represent how these charges interact together. So, how to draw electric field lines. There are three rules we're going to follow whenever we draw electric field lines. The first one is that all of the lines start on positive charges and end on negatives. Your electric field lines will never cross, and the amount of lines represent the strength of the charge. So down here I have two separate examples. This blue one is a positive charge. The first rule says lines start on positive and end on negative. So all of our lines should be coming out of the positive charge. Now with my negative charge over here on the right, it's the opposite. All of the lines come in to the negative charge. So let's do we already did these two, positive and negative. Let's do what it looks like when a positive and a negative charge interact and their electric fields interact. So here's my positive charge down here. Ooh. And here's my negative. Now these guys are going to experience an attractive force, right? They're going to want to come together. So their field lines should represent that. All of the lines should start on the positive charge and end on the negative charge. So what you're going to get is a bunch of field lines that look like this. Now, if the charges have equal charge, so let's say this is a proton and an electron, the amount of lines that are on the positive charge, all of them would go to the negative charge to show that the charges are equal to one another. And this is for an attracted situation. So let's look at what happens when we have a positive and a positive charge together. For a positive and a positive, these guys are going to want to repel, right? So their field lines should not come together. We're going to draw them almost as if there is an invisible wall right between the middle of them. The field lines will never cross each other, right? This is rule number 2. And they kind of press up against one another, right? They're showing this repulsion, this idea that they don't want to come and stick together. So this is what it looks like with two positives. Of course, two negatives would look the same, except the arrowheads would be flipped so that they're going towards the negative charge. And then the last one is, what does it look like when we have a larger charge and a smaller charge together? So let me pull up my other paper since I don't have any room. So let's say I have a positive here and I have a negative here. And let's say this is negative Q and this is positive. Let's say this one is, let's start it easy, 2 times the charge of this guy. So we're going to draw our lines just like before because it's an attractive force. The field lines are going to want to come together. But this guy here has twice the charge as this one. This means he needs to have twice the field lines. So if we look over here on our negative charge, he has 4 field lines. 1, 2, 3, 4. So that means that the positive one needs to have 8 field lines. 1, 2, 3, 4, 5, 6, 7, 8. And you can just draw them coming out here to the side. It doesn't really matter. So, just by looking at this picture, we know this is positive, negative, and this guy is twice the charge as this one because it has twice the lines. Alright, because we can't do anything in physics without some math, we're going to talk about how to find the strength of an electric field. The strength of an electric field depends on the charge that makes the field and how far away you are from that charge. Now this equation looks very similar to our electric force equation, but we're only dealing with one charge now. We only care about the charge that is creating the field. We don't care about the charge that's sitting in the field. All we care about is the strength of the field itself, which makes sense, right? The strength of the field would only be determined by the charge that's creating it, not by anything that's sitting in it, right? The amount of gravity doesn't change, right? No matter how much stuff we put on the Earth, the amount of gravity for the Earth is still the same. So same thing with the electric field. K is Coulomb's constant, just like it was before, 9 times 10 to the 9th. And R is your radius squared, just like it was before, the distance you are away from the charge. Electric fields are measured in what's called a Newton per Coulomb, or a force per charge. And electric fields are vectors, just like the electric force was a vector. So I know we did all those crazy problems where it was like this, and you got integrals coming out of this. We're not really going to get into that very much with the electric field part, but just know that you can. Because these guys are vectors, you can add them together. If you have 2 electric fields interacting, their strength can be vectorly added. But I just have a super quick math problem down here for you guys. A proton and electron are separated by a distance of 2.8 times 10 to the negative 12th. What is the magnitude and direction of the electric field set up by the proton at the position of the electron? So, our proton looks like this. We got lines coming off of it like this. We want to know what kind of electric field does this guy make. So, electric field is kq over r squared, with q being the charge of the electron, right? So 1.67 times 10 to the negative 19th coulombs. So when we do our math here, 0.67 times 10 to the negative 19th, divide that by the distance away, which is 2.8 times 10 to the negative 12th squared, we should get an electric field of 1.9 times 10 to the 14th newtons per coulomb. Now for direction, we want to say it is away from the proton. How do we know that it is away from the proton? Because our electric field lines tell us that the electric field is moving away from the positive charge. Alright, let's talk a little bit about this idea of electric potential energy. This starts chapter 18. We're just going to get into it a few sections here. When we discussed gravitational force, we talked about gravitational potential energy, right? This is a measure of the potential that gravity has to do work on you. So if you're standing up here at the top of a waterfall, we're just going to say this is a waterfall because it's blue, you have a lot of potential energy, a lot of gravitational potential energy. Gravity has a lot of potential to do work on you. It can pull you down to the earth really dang fast, right? Up here we say we have a high area of high gravitational potential, and down here we have a very low area of gravitational potential energy. Hopefully that's a review for all of you guys. When we talk about moving charges, we can talk about potential energy associated with that too, and we call that electric potential energy. So now you have two different kinds of potential. Actually, you have three if you count elastic potential, but we're not going to do that right now. So electric potential energy, this is the energy associated with a charge due to its position. Not a mass, it's associated with a charge in an electric field. So whenever a charge moves because of a force, its potential energy is either going to decrease or increase. And this works just like gravity. If, like I said before, if you climb higher up, your potential energy increases. If you go down, your potential energy decreases. Your potential energy depends on your position. The potential energy of a charge depends on its position too. So we can stick with that gravitational analogy, and we can explain what's happening to a positive charge when it's in an electric field. So things that go with nature, or things that would happen naturally, will decrease potential energy. It's very natural to fall when you fall from a ladder. You go from a position of high to low, and this goes with nature. This is what naturally happens. So your potential energy decreases. A positive charge moving towards a negative charge goes with nature and will decrease the potential energy of the charge. So if you have positive, negative, bloop, goes this way, that will result in a lower potential energy. So when the positive charge is way out here, away from the negative sign, we have a potential energy. We have the potential to do work with this charge if we wanted to, and we're going to get into that later. But as the charge moves closer to the negative sign, its potential energy is going to decrease. Its ability to do work, or its ability to have energy, is going to go down. So, back to the gravity example. On the other hand, if you were to take a rock and roll it up a really, really, really big hill, that takes a lot of work. So you have to put into that situation a lot of energy. So it does not happen naturally. So the fact that you have to put work into that system and it doesn't happen naturally, this increases the rock's potential. So same thing with positive charges. Bringing a positive charge close to a positive charge, well, this is going to require a lot of work. Either a lot of force on your part or something else's part to put these two things together. They don't want to go together naturally. You have to make them do that. And if you have to make something happen, you're going to increase its potential energy. All right, we'll talk about this concept and then we will be done with this video. This idea of electric potential. A more accurate way to talk about electricity is to discuss electric potential and potential difference. You guys probably know it as voltage. It's measured in volts, and the equation to find it is right here. Pretty straightforward. I call it the VED equation. The voltage is equal to the electric field times the displacement. And I'll explain what those things mean in 1 second, but I wanted to give you guys the equation first. So once again, let's revisit gravity. So let's say you have two rocks. One is very small, and one is very big. But you raise them up to the same height above the ground. Even though there's the same height above the ground, let's say this is 1 meter, they're going to have different gravitational potential energies, right? Because they have different masses. So it's really not correct or wise to say that this 1 meter height is an area of high potential energy. Because it's really not. It's really not an area of high potential energy. It's going to depend on your mass. So it'd be more accurate to say, or use a unit that describes gravitational potential energy per kilogram. So if we can say something has a certain gravitational potential energy per kilogram at a spot, that would be a more accurate way to describe it. So this is what voltage does and electric potential does to us, but it does it for us in the electrical sense. So electric potential depends on the strength of the electric field and the distance the charge is moving, but it does not depend on the actual amount of charge itself. And this differs from the electric potential energy, which does depend on the amount of charge. So it's a little bit easier to think of the electric potential energy as being a property of the charge, and the electric potential as being a property of the field. So, for example, I have this picture over here for you. You have a little Van de Graaff generator, all has positive charge. Two positive charges over here. If it's 1 Q, it'll have a certain amount of potential, but if it's twice that Q, it'll have twice that much potential energy. But the electric potential of both of these guys is the same, because electric potential is, oh, not EP, sorry. Electric potential is voltage, and electric potential is the it's the same for both of these guys here. The potential energy per unit charge is the same for both of them. Alrighty guys, I'm going to stop there because I am running out of time, but if you were super confused by this PowerPoint, don't worry. The idea of electric potential energy and electric potential and potential difference are all kind of confusing. It starts to become a little bit clearer when we start talking about circuits, but we will discuss this tomorrow and do some example problems together, so hopefully you guys will feel a lot more comfortable with it after tomorrow. But I will see y'all then. Bye!